Okay, basic steps for all programs. If you haven't written any programs before, don't worry about it. Just try to follow along as best you can, and if it piques your interest, then move ahead. Because in the end, anyone watching this probably won't have any trouble making the circuit. In other words, buying the components and wiring them up. Then all you lack is the program. And the program can be made available. I'm going to show you enough that eventually, if you watch, this video and maybe a couple subsequent ones, you can do the programming yourself or find somebody to do it. It's a simple program. It won't take much. Just relax and kind of go with the flow here. Well, if you know anything about computer programming or not, the very first thing you have to do is define your communications. I mean, you think about it, you got this little thing that you can put in your pocket that has, we'll call it a brain in it, a CPU, it's got memory. How do you get anything in or out of it, especially in it? If you write a program on your computer, you have to download that program into that little brain, that CPU and memory, and then tell it to run. So you've got to have communication. If you've written any code in the past, I don't mean, operated a computer. I mean, you wrote text programs. At the top, you always define the communications, the name of the port, and any configuration for that port, baud rate, checksums, parity, whatever. So you got to define the communications. Now, in this particular program, this device, it's really simple. When you first start your program, you're going to go tell it what port you want to use, and then it just does the rest for you. Defining the communications is real simple, but that's the first thing that always takes place when a program is getting built, is defining the communications. The second thing is going to be defining tags or pointers or variables. Those names are all the same thing. In the computer, the little computing device, you have a processor, but you also have memory. And the memory has memory locations. They're numerical in their structure, meaning that each word in memory has so many bits in it, and then the words are in an array. And you have to define any variables that you want to use in your program. In other words, if you want a variable that says at station, this is train station. In other words, you want a bit that says that it's at the train station or it's not. Binary. That's a bit. 0, 1. 0, it's not at the station. 1, it is. So you go in and you create a tag name, variable pointer, and you'll call it at station. And then you will define it as a Boolean. And then in the background, the compiler will determine where it's actually going to be in the memory. You'll never see that. You just give it a name and say what kind of data it is. And you have to have all these tag names and defined before you start writing your program. Otherwise, you got nothing to write. Then you write your code. That's probably the most difficult part because you have to think through what you're doing and you got to understand the language that you're writing the code with. In the flow chart that we're going to use, the flow chart programming, you could also call it function block diagrams in a sense. It's not really, but it's similar. But it's very graphic. It's relatively easy to understand, and once you go in and you do something simple, which we'll start out doing, then you're going to find that you can handle this. Okay, once you got your code written, then you're going to debug it. Okay, and the program that we're going to use with the ACE, I think it's called VBuilder, Velocity Builder. It allows you to put it in the debug mode and you can execute your code right on the screen, not controlling the train or anything, but right on your screen to see if it does what you expected it to do. Then you're going to hook it up to your train track and you're going to commission it, meaning the code behaved the way you thought, but then once you start running it, now you say, oh, I should have made that longer, I should have made that shorter, I should add this, I should add that. That's kind of what follows after debug, or that's called commission. This is the same thing out in manufacturing. I've got thousands of hours out on the shop floor in different manufacturing plants. I mean literally thousands of hours doing debug and commission. What you're going to learn right here is what you would do if you became a controls engineer, and we're going to go out there and do it on the shop floor. Okay, let's start by talking about assigned memory locations, because remember it was communication, then it was your memory locations. Variables, pointers, tags, aliases, that's all the same thing. But at the root here, you will never actually know the real memory location. It's numerical in nature, and it is an array of words in memory. It's electronic, it's solid state, but your compiler does that for you. You're not going to see that. You just come up with what you want to call it and define it as a data type, and you're done. But all these terms right here, variables, pointers, tags, aliases, they're all the same thing. But they all describe name that we define as a data type in a different way. Variables means it can vary. Pointer, it points to the real memory location that you don't know. Tags, you tag it when you're programming. Alias is kind of secondary in that in some programming you can create a tag, or you get a predetermined tag that the manufacturer determined that you're going to use, and you can give it an alias, meaning it might have been called I058788 and you want to call it Monkey Doodles. Monkey Doodles is the alias for the tag name that you gave you. Let's not belabor that. But memory locations basically have tags. That's what we'll call them. Okay, we'll start out with the first group. If you were to open up the tag database for this particular software, vBuilder, and select the very first one, input bit. Now remember, we're using the ACE 11. Now I'm using the 14, okay? But you've only got 6 in and 6 out if you're using the ACE 11. That first name up there, it says C1 start push button. That did say in bit C1, like in bit C2, 3, 4, 5, and 6. I changed the name. I left C1 on there just when you're looking at it in the program, you know it comes from IO port C and it's the first bit. Now remember, in the computer it's 0 through 5, not 1 through 6. It's always debatable. Do you make this C0 through C5, which is 6 of them, or 1 through 6? Well, people like 1 through 6 better than 0 through 5. I renamed C1 start push button. Okay, and that's the only input that I'm going to have initially. Then I went to the output bit. And here I've used the first, because it's D1 through D6. This is the 1430 here. So my output bits, the 11 doesn't have this many output bits, okay? See, because it's D and E. All you've got, if you're using 11, I think is D, or however it's designated. I renamed the first 4 outputs at station, meaning when I turn that bit on, I want to hear the sounds from a locomotive at 7.5 volts that it's at the station. It's sitting there idling. And then the next one, D2, I named that accelerate. That's when you increase the voltage just enough to get it to start moving, the bell's dinging, and you got a couple toots out of it. And then the third one, that's my cruising voltage. When I increase up to 11 volts or whatever, it picks up speed and then it cruises. You don't hear the bell anymore. All you hear is the chuff. And then when I want to go back to the second one up there, accelerate. In other words, I want to hear the sounds that it makes when it's running slower and you can hear the bell and everything. That I call decelerate. It goes from cruising speed back down to the decelerate speed, which the sounds are the same though for D2 and D4. But remember, I told you there's a little hysteresis in the way the voltage works to get the sound. I needed a fourth one to make it more realistic. And then I've also got a timer. I'm using a timer to control this sequence, and I might make the timer 2 minutes, 120 seconds. And within that 120 seconds, I will cycle through these different outputs, D1 through D4. For the first 5 seconds, I might have the station sounds. And then I turn off D1 and turn on D2, and it starts moving, chuffing. You're getting the bell and the whistle. And I might do that for 10 seconds. And then I bump it up to cruise for a minute or more. And then when I want to stop at the station, I go back to the lowest voltage, around 7.5 volts. That's the decelerate, D4. And it stops, it decelerates down to the same speed it was going with D2 accelerate, making the same sounds, the chuffing, the bell, maybe a whistle or something. And then when I'm ready to stop, then I go to D1 at station. The locomotive stops, it sits there, and makes the station sounds. Okay, but that's my timer up there. Under I-32, I have a timer. Now I'm assuming that means 32-bit, which is a double integer, and that gives you one huge value that you can increment up to. And this timer is a little bit different than timers in PLCs. You just start it and it keeps on going, and you have to use certain instructions to read it, and you need a reset to stop it. Okay, we got one input, a start push button. We got 4 outputs for the 4 relays. They're going to switch different voltages onto the track. And then we have a timer. And last but not least, we have a bit. You're thinking, well, the first 2, those were bits. Yeah, input bit is associated with an actual hardwired input, output bit, hardwired output. But straight up bit is an internal bit that's not connected to anything. But you can control it in your program. And you'll see here shortly what we do with start sealed in. I need a bit in memory that when I start this thing running, that it will seal that bit in. And even though I remove the start, it's still on, sealed in. Okay, let's program a sequence with one timer. We're talking about one timer. And we will start the program running with a momentary push button. Let's begin with how we want the program to react when you press and release the push button. And you see 3 pictures there. And this is a normally open momentary push button. At rest, when a device is at rest, it's in the normal state. When no one's pushing the button, that contact block on the back there, the green thing, that's open. If you push the button, it closes. If you release it, it goes back open. Simple enough. Okay, let's start by how do you seal in a momentary push button. In other words, you pressed it and something initiated, and when you release it, it keeps on going even though you no longer push the button. So let's look at our first little chunk of code there. And we have decisions and actions. They are binary decisions, and then you have 1 or 2 actions. So we have 2 decision blocks there. The first one says is start sealed in on. And then you see a yes and you see a no. All decision blocks are binary in that if it's true, then it does the yes thing. If it's false, it does the no thing. But it's going to go 1 or 2 directions. If it's yes, then it goes over to start and starts the timer. No, then it resets the timer. That's simple. Decisions and actions. We have a second decision block down there that says, is the push button pushed? Yes, then turn on start sealed in. Now go back to the top decision that says, is start sealed on? Start sealed in, is it on? No. Reset, is the push button pushed? No. Then it goes back to the top and it just sits there and it cycles between those 3 instructions. When you power up your little controller here and you haven't pushed the button yet and you leave it this way for a week, that's what it sits there and does for a week. Is sealed in on? No. Reset complete sequence. Is the push button pushed? No. Go back to the beginning. Is start sealed in on? No. Complete sequence reset. Is input bit C1 the push button on? No. Now, at some point you're going to push the push button, and when you do, something's going to happen, hopefully. What's misleading here is that top decision doesn't go green right away. The bottom one goes green first. Okay? If you look at those 4 instructions vertical there, start sealed in, yes, no, no, reset complete sequence. Is the push button pushed? No, it cycles back to the top, like in the first diagram. But if it is on, then it starts sealed in, and it goes back to the top, and now that's true, because you just started it down there at the bottom. In less than a thousandth of a second, when you push that button, both of those go green. You're not going to see that top one red and the bottom one green, not unless you got some freak occurrence in the refresh of your monitor. We don't want to get off talking about, refresh rates and what you see on the screen versus what is really happening. Anything that's momentary, like less than a thousandth of a second, you're just not going to see it on the screen. The result is, though, as long as you're holding the button down, then it's going to go, is start sealed in on? If it's yes, then it's going to go to start. But let's pretend like for one program scan that was still false up there. I can't screen capture it. When you first push that push button, it's the way it is over here on the left, but that bottom red one turns green. It goes down and turns on start sealed input, start sealed in bit in memory. Then it goes up to the top. Then you go next door to the middle one on the screen. That's now green, and it's going to actually go off to the right to the start complete sequence action block. This path you see right here of going down through the decision blocks all the way to turn on and then back up to the top, that's only going to happen for 1,000th of a second. But I needed to show it to you. As long as you hold the button down, though, eventually in my code, I won't let it continue until you release it. But for right now, you just started it. Okay? The first diagram with both red decision blocks, they just sat there and cycled in that until you pushed the button. When you push the button, in less than a thousandth of a second, both of those are going to turn green, and then it's going to go to the third diagram when you release it. Okay? Now, right now, if you don't release it, if you press it in diagram 1, then for 1,000th of a second, it does the one in the middle, and then it goes to the one all the way to the right. And it basically, that's what it does whether you release it or not. Later on, we'll do more with this. So that's real simple code right there. All this is how do we press a button to start something but have it continue. In other words, we don't want to hold down the button, and we don't want to switch where you just switch it on, like a selector switch, like a light switch. We want to press a button and have it run and not hold the button down. Okay, now notice that the tag names were shown here. Look at all those blocks. You got decision blocks, they're red and green, red or green, and then you got kind of rectangles, those are actions. Now notice that all of these instructions right now have the tag name in there. Start sealed in, complete sequence, input bit C1. Now I noticed that it says input in bit C1. I now changed that to C1 start push button. That is a slight discrepancy here, but it's irrelevant. It behaves the same. Those are the tag names. Now let's look at this again, but with the values shown. Here I'm showing you the exact same diagram, but notice instead of tag names in there, it's showing you that the first one, that it's 0. The second one is 0. The third one is 0. The fourth one is 0. And then the start is also 0. If I push the button, now notice that the top one is 1. The middle one, the reset and the start, both those actions show the current value of the timer that it's accumulating. And I do believe that's 3.241 seconds or something like that. I've never really looked at the time base on this particular controller, but that is between 3 and 4 seconds. So the 2, 4, and 1, that would be a fraction. Okay, so you see the difference is here we had the variables shown, the tag names. If you go up and click a button up in your software, you can switch from the names to the values. Okay, then we push the button. Now notice they both show 1. Then we release the button, and instead of just seeing the tag names, you see that the first decision block, it's on, and then the action is 33807. That's at 33 seconds. So you see 30 seconds lapse between these screen captures. I hope this does it for you. Let's keep moving. Okay, now let's look at the whole code for this application. Now, I'm going to modify it later as we go, but let's keep it simple. You see the first part there that has the two red decision blocks, and to get out of that loop, you're going to go through the start, and then you're going to start looking at other decision blocks, looking at the amount of elapsed time on that timer called complete sequence. Okay, the button's not pushed. We push the button, it's held down, and notice that both of those first two decision blocks, they go green because you're holding the button down, but you did start the timer, and now it's starting to execute the blocks, the stack over to your right. 1, 2, 3, 4, 5, 6 green ones and a red one. Okay, if you release the button, everything continues. The only difference is both of the first two decision blocks are green, now just one of them. When you release it, and after 5 seconds, you look at that top green decision block that's still green. It says, if the timer is less than 120 seconds. The whole thing is 120 seconds. If it's less than 120 seconds, then it goes down. If it's not, then it goes over and turns off, start sealed in. And that's the end of the sequence. At the end of 120 seconds, this decision says, is it less than 120 seconds? This decision block, notice it's got a little alarm clock on it. That tells you that it's looking at a timer. See the timer right next to it? The start action block, it's got a little alarm clock. That means it's a timer. And all these comparisons are looking at the time and saying, the first one says, is it less than 120 seconds? Well, you just push the button. Of course it's less than 120. The answer is yes. It goes down to the next block, and it says, is it less than 5 seconds? If it is yes, then turn on at station. That's going to energize relay D1. You're going to start getting station sounds. Okay, then, and it'll do that for 10 seconds until you reach 15 seconds. Is it less than 15 seconds? If you go back up here to yes, if it's less than 15, then turn off the at station and turn on the accelerate relay. That gives you those sounds. And after 10 more seconds, or 15 total, it's no longer less than 15. Now it's less than 100. Now you're going to turn off accelerate, relay D2, and you're going to turn on D3 cruise. Now you're going from 15 to 100 seconds. When it gets over 100 seconds, now you're going to the next one, and it says, is it less than 110 seconds? If it's less than 110, then it's going to divert the decision over to turn off the cruise and turn on the decelerate, and then loop back to the top and keep cycling. Then after 110 seconds, then it goes to the next decision block, because all those one above it, notice the top green one, that if you go off to the right, that's no. You go down, it's yes. But look at all the rest of them. They're all yes, go to the right, no, go down. Don't get too confused here. You pick which way is yes and no. The first one we're saying is the whole sequence done. If we said, in other words, less than 120, basically it's saying, have we completed the sequence yet? But the answer is it less than 120? Be careful how you word things. But notice the yes and the no is on the opposite corners, if you wanted the diamond. That one's going to stay true up there. That top one will stay true until you complete the whole sequence. And then it's no longer less than 120. It says, is it less than 120? When it hits 121, no. Turns off the sealed in, cycles back over, and the one that's green there over to the far left is start sealed in on no. Okay, reset the timer is the push button push. See, you start all over again. So you get down to the bottom there, and after 110 seconds, it's going to go for 5 more seconds. It turned off decelerate, and it turned on at station. It turned off decelerate, and it turned on at station. Okay, now, after 115 seconds, so to speak, for 3 seconds, that bottom one's going to be green because it's less than 118, then it's going to say, no, it says greater than 118. When it's greater than 118, yes, turn off at station, turn off. Start sealed in, goes back to the top, and you're done. Okay? Now, both of those should have been 120. The one on the top and the one on the bottom. It really doesn't matter. That just means that when it turned on the at station sounds, I only got 3 seconds. Then after 118 seconds, this becomes false. Okay? Well, actually, it becomes true, but you'll never see the transition, because when you hit 118 seconds, see, it says, is complete sequence greater than or equal to 118. The minute you hit 118, then you're going to turn off everything and reset it, but you'll never see the change other than it just resets.